defined this idea of things being equivalent modulo some divisor. That's very small, isn't it? And in particular, we then proved a whole bunch of properties about this modular equivalence, right? So this theorem just kind of says, here's a different way that you could think about it, like this is equivalent, so we could maybe sometimes use that to prove things about it. And then we proved a whole bunch of properties. So we proved, well, some of them we proved, some of them we just stated, but I claimed that we could prove the other ones. So it's reflexive, it's symmetric, it's transitive, just like normal equality is. And then also, proved it's transitive. Also, I stated, but we didn't prove, that it is a congruence with respect to addition and multiplication. And did I actually prove? No, we didn't actually prove that. Okay. So I think maybe what I want to do, I want to start by proving maybe part 2, and then kind of think about the proof and think about why this isn't true for division. Unlike normal equality, I can do whatever I want to both sides of an equation, and if I do the same thing to both sides, it's still going to be true, right? But that's not for this modular equivalence. There's certain things we can do to both sides that will preserve it, but certain things we can't. I'll think of what those are, and then we'll do some examples like kind of using this to solve equations, but equations actually up to some modular equivalence. All right. So any questions about that so far? So right, so I'm going to pick this up and say this theorem. This is from last time. Given A, B, C, D, which are integers, and M, which is a positive integer, if A is equivalent to B and C is equivalent to D, then AC, or I'll say 1, A plus C is equivalent to B plus D, and 2, AC is equivalent to D. So let's just prove 2. And it's actually, the proof is going to be kind of similar to the proof that we did before. Just another example. So, say, since A is equivalent to B, there exists an integer j such that A equals B plus Jm. Right? This is a theorem we proved that we said A and B being equivalent modulo M. Another way to say that is we can get from one to the other by adding some multiple of M. Right? So their difference is the multiple of M. Likewise, there exists some K such that C equals D plus Kn. Okay? And now, I want to say something about AC and BD. So, AC what's my goal? My goal is to prove that AC is equivalent to BD mod M. And one way we could show that is if AC is equal to BD plus some multiple of M. And so actually, I'm close, right? AC is equal to BD plus some stuff. Is this stuff a multiple of M? It is, because I can factor out an M out of everything there, right? So I can say this is BD plus M times BK plus JD plus JKM. Hence, AC equals BD plus a multiple of M. So, AC is equivalent modulo M BD. Okay, any questions about that? So let's think what would go wrong if we tried to do a similar proof for division. So if I wanted to say, you know, if A is equivalent to B and C is equivalent to D, then A divided by C is equivalent to B divided by D. I could start the same way, and I'd say, well, like, you know, A equals B plus JM, C equals D plus KM. Then I'd say, well, A divided by C is B plus JM divided by D plus KM. But then I would be kind of stuck. Like, that wouldn't be B divided by D plus anything. So, all I need to say, note, we get stuck if we try the same proof for division. You know, A divided by C equals B plus JM divided by D plus KM. Right, but this does not look like B divided by D plus a multiple of M. So it's kind of because, like, this modular equivalence is kind of defined in terms of plus, like, addition and multiplication, right? There's addition here and multiplication here, and those sort of play nicely with when we do this, when we multiply two things or when we add two things. When we divide, it just doesn't really work. And so now this doesn't prove that it's false. Like, this isn't an argument showing that you know, maybe we just aren't clever enough and we have to come up with a different way to prove that it works for division. But it actually is false. So let me show you an example. So in fact, it is false. For example, let's see what would be a good example. 2 is equivalent modulo 4 to 6, right? Because you could think of it as like they both have a remainder of 2 when you divide by 4, or you could think of it in terms of, you know, they're separated by a distance of exactly 4, and so they're kind of in the same place in the cycle, right? And obviously 2 is equivalent to itself modulo 4. But if I divide these, 2 divided by 2 and 6 divided by 2, right? So I have like, you know, 2 and 6 are equivalent, 2 and 2 are equivalent. When I divide them, what do I get? I get 1 and 3. Those are not equivalent modulo 4s. right? So this is equal to 1, and this is equal to 3. Right, 1 and 3 aren't the same modulus. Okay, so in general, we cannot divide both sides of an modular equivalence by the same thing. Does that make sense? So with equals, with actual equals, because it means they literally are the same thing, we can do anything at all to both sides of an equation. But this isn't literally equals, right? It's saying, well, these things are the same in some way. They're not exactly the same, but we're considering them the same. But we have to be more careful now what we're allowed to do and what we're not allowed to do. So we're not allowed to divide. It turns out there are some situations where we can divide, and we'll get there in a while, not today, but to figure out like when that is allowed and to prove that that works in those cases, but it doesn't work in every case. All right, so I want to do an example where I'm going to solve an equation, except it's not with equals, it's with modular equivalence. So I'm going to solve the equation, or I guess I should call it an equivalence, not an equation. 4x plus 7 is equivalent modulo 3 to 12. Okay, if this was an equals, we all know how to solve that, right? And the way we solve it is going to be similar to how you already know, but we have to think a little bit more carefully about what we're allowed to do. So, any ideas? How do you think I should start? I mean, let's ask this. How would you start if it was just an equals?
Subtract 7 from both sides.
Subtract 7 from both sides. Okay, so the question is, are we allowed to do that here? Jared says,
I think so.
you think yes?
You like adding negative.
Okay, so we could, subtracting 7 from both sides, we could think of it as adding a negative 7 to both sides. So are we allowed to add the same thing to both sides? We are, right? So that this theorem, well, I didn't prove that part of it, right? But one part of the theorem says, you know, if you've got two things that are the same, you can add them. And of course, you know, a special case of that is if I have like, if C and D are actually the same. If it's like A is equivalent to B and C is equivalent to C. Well, C is always equivalent to C because we proved that this is reflexive, right? Things are always equivalent to themselves. So then, in that case, this is just saying that I can add C to both sides, and that would be okay. So yes, I'm definitely allowed to add the same thing to both sides, which means I'm also allowed to subtract from both sides, because subtraction is really just addition, and you're adding a negative. So, note, we are allowed to, or actually, you know what, I'm going to put this, I'll just say this implies that 4x is equivalent to mod I, and negative both sides. you're doing problems like this, you don't have to like cite the theorem. You can just say, yeah, subtract 7 from both sides. But the point is, I want you to understand, that we have to think carefully at first. Once you build up an intuition and you've seen the examples, you'll just know, oh yeah, I can do this, I can do this. But fundamentally, the reason we can do those things is because we've proved some theorems saying that this has certain properties. Right? What you would do if this was an equals at this point is divide both sides by 4, right? But we already said we can't do that. And in this case, we would get like 5/4, which wouldn't even really make sense because we're kind of just working with integers at this point. Is there anything else we can do to simplify this? Here's something I can say. If I asked you like 5 is equivalent modulo 3 to what? What would you put there? Is there something else you can say that's simpler that 5 is equivalent to? 2? Yeah, I agree. Right. 5 has a remainder of 2. And you divide by 3. Or it is 2 more than a multiple of 3. So that's equivalent to 2. I mean, there's lots of things that it's equivalent to, right? It's also equivalent to 8, or to 11, or to -1, right? But 2 is probably the simplest thing we could say. If we do 5 mod 3, and we get that remainder that's between 0 and 2, right? We get 2. So, okay, well, if 5 is equivalent to 2, and 4x is equivalent to 5, right? Because this equivalence is transitive, I can say, well, I can reduce the right-hand side and say this means really that 4x is equivalent to 2. Right? I can, formally I'm using transitivity, but I can just think of it like, oh, I can always just reduce something by, mod 3, and it'll still be equivalent. Put another way, saying that something is equivalent to 2 modulo 3 is the same as saying it's equivalent to 5, because 5 and 2 are the same. They're the same in terms of their remainder divided by 3. Okay? Can I do something similar to this side? Can I kind of reduce that at all? Well, so 4 is equivalent modulo 3 to 1, right? Then the question is, well, but I don't have 4, I have 4x. So, can I do something with that? Well, yes, I can, because of this theorem, right? If 4 is equivalent to 1, and x is equivalent to x, then I can say 4x is equivalent to 1x, because I'm always allowed to multiply. Right, so I can say 4 is equivalent to 1, and x is equivalent to x, so 4x is equivalent to 1x. So that means I can just replace this by x. point of this is, when I'm dealing with equivalence modulo 3, I can always just, I can go through, if I have a bunch of stuff added and multiplied, I can just go through and each individual thing that's being added or multiplied, I can just reduce it individually. Because I can put them all together using addition or multiplication, and that works. Okay? So this would be a good way to write a solution. So notice this actually isn't a single value for x, right? This is actually saying, right, this actually says x really means x is an element of this set of all things that are equivalent to 2. So it's like, you know, negative, negative 4, negative 1, 2, 5, 8, 11, dot, dot, dot. And we could try one, like let's try 8. So if I put 8 in here, 4 times 8 is 32, plus 7 is 39, and 39 has a remainder of 0. It's a multiple of 3, so it has a remainder of 0. 12 also is a multiple of 3, has a remainder of 0. So 39 and 12 are indeed equivalent modulo 3. And any of these things you put in there for x, you would get, like this would be true. Those would be multiple of 3. And it turns out these actually were all if and only ifs, so these are the only possible solutions for x. Any other number you put in there won't work. One more example. 5x plus 17 equivalent to 5. All right, well, this time I'm not going to bother writing all the reasons for each step. We'll just do it. So I could start by, what do you think? How should I start? Add 2 to both sides, sure, I like it. So this says 4x plus 19 equivalent modulo 5 to 14x. I'm certainly allowed to add the same thing to both sides. Okay. Now what? Subtract what?
4x.
Subtract 4x from both sides. Okay. So 19 equivalent modulo 5 to 10x. Now what? Dora? Okay, so 19 is equivalent to 4, so I could certainly do that. What next? Dora? actually didn't intend to do that, but it's a good example. Yeah, it just turns out, no matter what value of x you put into that original equation, it's never going to be true. Well, let's do another one that does have a solution. So I'll just change this slightly to do 4x plus 17 is equivalent modulo 5 to 15x minus 2. How about that? So I won't make you all, so 4x plus 19 equivalent modulo 5 to 15x. I added 2 to both sides. I'm going to subtract 4x from both sides, 19 equivalent. You know what, I'm going to do several steps at once. This is the same as 4, equivalent modulo 5 to 11x, which means 4 is equivalent modulo 5. So 11 is equivalent to 1 modulo 5. So that just means x is equivalent modulo 5 to 4. A solution. You know, and we could try, if we wanted, like, if we put 4 in, actually, you know what, it'd be simpler. So negative 1 is also equivalent to 4 modulo 5. So negative 1 could be a solution for a potential solution for x. If I put negative 1 in here, I get 17 minus 4, that's 13. And over here, I get negative 15 minus 2, which is negative 17. Are those equivalent modulo 5? Well, if I, let's see, what did I say, 13 and negative 17? So yeah, the distance between those is 30, which is a multiple of 5. So, that's what it is. Okay. Why would you want to solve equivalences like this, other than the fact that someone tells you to do it on homework? I mean, you might care about something like this. One place this comes up that we'll see is when you have multiple things that are going in cycles, but at different rates. Like the cycles take different amounts of time, and you want to know kind of like when will they line up, or you know, how many times should I wait for if I want this one to be in a certain position, how many times do I have to wait for this cycle to go around? Which you could imagine coming up if you're like making some machine with gears or something, and you want to know like, you know, the gears are going around at different rates. Or if you have some kind of algorithm that's where things are looping through some array, different rates. We'll also see that, like, just trust me that this kind of thing is the basis for, like, the kind of skills that we're building here is the basis for the way a bunch of encryption works. So that's another reason you might care, although it's not as obvious. Anyway, cool. Any questions about that? So actually, I wanted to do one more example because I have 16x there, right? So we do a bunch of steps at once. If I add 2 to both sides, I get 19, reduce, I get 4, is equivalent modulo 5. Subtracting 4 from both sides, I get 12x, which means 4 is equivalent modulo 5 to 2x. Right, the previous examples I chose carefully so that we just ended up with x. But here, I have 2x. And again, if this was an equality, you might think to divide both sides by 2. We have to be careful here. It turns out, in this case, we would be able to divide by 2. So x is equivalent to 2 would be a solution. But I'm not going to do that. I'm just going to say question mark. For now, we don't know how to do this. I don't know how to simplify this. again, it turns out, for this particular one, that we would be justified in dividing both sides by 2, but we don't yet know, like, under what circumstances we would be justified in doing that or not. You can just try it, and you can see that x is equivalent to 2 is in fact a solution. You tried some examples, but not in general. Where we can't divide both sides by 2. And actually, maybe a better example, if I change this number slightly, I changed it to 16. So now when I add 2 to both sides, I get 18, which is equivalent to 3 modulo 5. Right, so now we really don't know how to solve this, because now dividing by 2 really doesn't make sense, because I would end up with 3 halves over here. And what would it mean that x is equivalent to 3 halves, right? Because we've only defined this equivalence for integers. And so that would not really be a valid solution for x, because we're assuming that x is an integer. Right, and x has to be an integer. So we will eventually, over the next week or so class, we will figure out how to solve this kind of thing, but we don't know how to do it yet. Okay. That's all I wanted to say about that for now. So in the last 15 minutes, I'm just going to introduce a new topic that we're going to spend some time on, and it's very related to what we've been talking about. And it may not be immediately apparent at first what the relationship is, but we'll see that the modular equivalence stuff returns. So, and this is the idea of prime numbers. And you all know about prime numbers. So, in some sense, I don't need to tell you what they are. But again, a theme of this class, I think, is that a lot of things that we're doing, maybe you've seen before in some form, but maybe you haven't studied them, at the same level of formality. So, what is a prime? An integer p greater than 1 is prime if and only if the only factors of p are 1 and p. And you've probably seen a definition like that before. Right? A prime is something where, the only divisors of it are 1 and itself. So that is, another way I could write this is, for all d, if d divides p, then d equals 1 or d equals p. Does that make sense? Right? If I have a number that divides p, then it turns out that has to be either 1, okay, and then integers greater than 1, which are not prime, are called composites. Or composite? I don't know, honestly, I think you can say it either way. Okay. Questions about this definition? So pop quiz, is 1 prime? No. Right, the definition says p greater than 1 is prime. Is 1 composite then? definition I wrote, no, it says integers greater than 1. So, note, 1 is neither prime nor composite. Right, 1 is special. 1 is, it is the multiplicative unit, right? It's the number that when you multiply by it, nothing changes. I think you'll find that historically there was a period where people used to call 1 prime, but we'll see in a little bit that there's good reasons for not calling it prime. It does behave very differently than the other primes. And if we called it prime, then we would have to be, like, there'd be a whole lot of theorems where we would say, you know, for all primes except not 1, blah, blah, blah. We have to put in all these special cases to, like, say we didn't mean 1. So it's like, well, if we're going to do that anyway, then why not just say, no, 1's not a prime, 1's special. Okay, and of course, what's special about primes? And you probably already know this, right? Primes are special because they are kind of the building blocks of the natural numbers, right? Any natural number I can express as a product of primes, right? So you've probably done like finding the prime factorization of things, right? Just ring a bell. So if we're talking about adding, then I guess I would just say like 1 is the only building block of the numbers when you're talking about addition, because I can just keep adding 1 plus 1 plus 1 plus 1 plus 1 to get whatever number I want. If I'm talking about multiplying though, in order to get whatever number I want, I need to have all the primes, and I can choose some of the primes to multiply, and I'll get any number I want. So primes are the multiplicative building blocks of the natural numbers. That is, we can actually make this precise. This is a theorem. Theorem. This is called the Fundamental Theorem of Arithmetic, which tells you something about how important it is. Here it is. Every positive integer, I guess I should really say like n plus, not 0. Every positive integer can be written as the product of 0 or more primes. So maybe this raises the question for you. What is the product of 0 primes? Any ideas what that means, or why I said 0 or more? Garrett?
2 times 2 is 4. There are 0 primes being multiplied there.
2 is prime.
Oh, I'm an idiot. That's fine.
So here's the question: if I let's do this. Matthew,
What did you want?
what do you mean?
Like the product of, yeah, it's 0 primes.
The product of 0 primes would be 1. Yeah, I think so. So if I have an empty set of numbers, so it's a set of numbers, but it's empty. There's no numbers in it. If I add all the numbers in the set, I get 0 because I have nothing to add. So I just have 0. However, if I multiply all the numbers in an empty set, I would argue we should get 1, not 0. Because 1 is the multiplicative identity for multiplication. 1 is like what you start with when you haven't done any multiplication yet. Right? I start with 1, and then if I get a number of 2, oh, now I do 1 times 2, and now I have 2. Then I get another number 3. Do 2 times 3, I get 6. If I started with 0, I would always have 0. No matter how much I multiplied by stuff, I would just always have 0. So 1 is the appropriate thing to start with, to say, if I haven't multiplied anything at all, I have 1. This is also why, like, something to the 0 power is 1. You probably learned that rule, right? It's because, well, what's 2 squared? It's 2 times 2, that's 4. What's 2 to the 1? That's just a single 2, that's 2. What's 2 to the 0? Well, 2 to the 0 means I'm multiplying no things at all. I'm no copies of 2, and that's 1. So, the reason we say 0 or more is because, 1 is the product of 0 primes. So, it's just an elegant way to include 1 in this theorem. Here's another question for you. If I have some number, could I have multiple different ways to write it as the product of primes? Like, could I have a number that has 2 different prime factorizations? Just, what do you want to say intuitively? Like, what did you learn from, middle school?
I want to say no, because the purpose of a prime factorization is to simplify every number as much as possible.
Okay. So you think no, you can't have a number that has 2 different prime factorizations. Okay. Anyone else agree? Disagree? So how about, here's a question for you. How about 2 times 3 and 3 times 2? They both equal 6, right? So those don't look literally the same. Should those count as 2 different prime factorizations or not? What do you think? Max, you're shaking your head no. Why not? Why do you think we shouldn't consider? I agree. Why do you think we should not consider those different? Right, that's right. Yeah, and because multiplication, the order doesn't matter, so yes, since I'm using the same numbers, it doesn't really matter what order I'm using. Great. Yeah, so, and it turns out, yes, Mason was right. Like, the prime factorization for a given number is unique if we have to say that we don't care about what order they come in, right? If you care about the order, well then yeah, you could write down lots of different, you just put them in different orders, but, so, I'll say, moreover, let's see, the product is unique if, we don't care about order. Or maybe you could say, if we always list the primes from smallest to biggest or something, that would make it totally easy. So, yeah, this is a really, it's called the fundamental theorem of arithmetic. It really is very fundamental because it says, in some sense, if we're studying natural numbers, we're studying positive integers, it's often enough if we kind of understand how things work for primes, then we can extend that to understand how things work for all the numbers. Because any number we can, break it down in this unique way into some primes multiplied together. And, right, the fact that it's unique, right, means that there's only one way to do it for any number. And that's not obvious. I mean, maybe it feels obvious to you because you've spent a lot of your life, in school kind of using that fact, but it's not. I mean, I don't know, why should that be true? Maybe there's some really big primes you multiply in a certain way, you get the same thing as some other primes multiplied together. I mean, why not, right? But it turns out no. It's unique, that's never known. So we can't prove this yet because, again, this needs induction, but we'll probably do the proof later.